Okay, first of all, thanks to the organizers for doing such a great job giving us a fun workshop over the past couple of weeks that I've been here. If I knew I would be following Andrea and Renata, I would have talked about non-canonical kinetic terms myself. But instead, I'm going to talk about lattice simulations in natural inflation. This is work that I've been doing over the past few years with Peter Atzhead at UIUC, Tom Giblin at Kenyon College, and Tim Scowley, our grad student, who is working while Peter and I are having fun. So, big thanks to all my collaborators. So we have heard very many experimental talks about trying to squeeze the tiniest bit of information we can out of the CMB, both from data we already have and from planned missions, and trying to condense them down to the bare minimum that I need for this talk. We're looking for tensor modes and scalar modes. So tensor modes in general models probe the Hubble scale during inflation, or the energy scale of inflation, and tensor modes are scale like the Hubble to the fourth over the field, the infrared field velocity. So the tensor scalar ratio is in some sense a measure of the normalized or non-dimensionalized velocity of the inflaton during inflation. So assuming that some of the bicep data is not dust, so assuming that CMB stage 4 actually finds R to be 0.05 or 0.03, so close to the 0.1 ballpark, it will lead to super-Planckian field excursions. Now, that slide would have been okay a week ago, but now I have to remake it and say that large R values at best suggest, are you happy with that? Suggest super-Planckian field excursions, although we have seen that there are very nicely motivated and very fun models that can give large R without that from other sectors. So the problem with super-Planckian field excursions is that they can suffer from UV sensitivity. So a nice idea that came out in 1990, if I remember correctly, was the introduction of shift symmetry. So we're using axions essentially to drive inflation, and the nice thing about shift symmetry is that it restricts the potentials you can have, so it essentially forbids all the higher order Planck suppressed operators that can spoil the flatness of the potential. However, shift symmetry has to be softly broken if you are to have any successful inflationary model. And there are many ways that you can think about breaking the shift symmetry, such as radiative corrections, non-perturbative effects. So, quadratic inflation, we know it doesn't work for the data, but it's still, a very good toy model for what I'm going to say. If you want me to talk about kind of more realistic models, please ask me during the question round. So, a nice thing about shift symmetries is that it also restricts severely the couplings you can have to other fields. So here I write down the lowest dimension 5 operators that couples gauge fields and fermion fields to the axion dash inflaton. And you can see both of them are derivative couplings, d mu phi, d mu phi, and derivative couplings obviously respect any shift symmetry. Now, since the conference is called Cosmology in the Light of Data, I want to point out that both these couplings give new experimental handles on data beyond the CMB, such as magnetogenesis, baryogenesis, leptogenesis, and so on. So, due to the interest of time, I will only consider coupling to gauge fields. Again, if you want to talk about fermions, ask me later. So we have heard a talk already yesterday by Lorenzo Sorbo, about what happens when you couple an axion to gauge fields. You see that the gauge fields start to be parametrically, tachyonically enhanced. Here I plot just a cartoon picture of what you expect. The green and the brown curves are the two different polarizations of my U1 gauge field. And you see one of them, both of them grow, one of them grows by orders of magnitude more, and it grows exponentially towards the end of inflation. Now, whenever you get something that grows exponentially, you have to start wondering, okay, are there back reaction effects? Well, yes, there are. So the produced gauge fields back react on the inflaton, and this is the equation of motion for the inflaton fluctuation delta phi. And you see here the kind of harmonic oscillator looking like equation and a forcing term, which is due to those exponentially enhanced gauge fields. The interaction vertex is the same as the one we use to hunt for solar axions. In that case, we have a B field, an axion from the sun scattering off to produce a photon. Here we have this exponentially enhanced gauge field scattering off the inflaton producing inflaton fluctuations. Now people in this room have done a lot of heavy lifting to calculate this sort of effects, like Marco, Lorenzo, Andre. And the two effects that can arise are non-Gaussianities at the CMB level, because this forcing term gives a non-Gaussian contribution to delta phi. And toward the end of inflation, where you can see that the amplification it's much bigger, back reaction can seed large fluctuations in the density spectrum, which can lead to black hole formation. So we want to be safe from those effects, so not spoil the CMB and not overproduce black holes. So we safely keep our couplings below the current limit in the literature, which is roughly 110 inverse M Plancks. However, we do want to go as close to that as possible to see what happens, and that way we're going to use lattice simulations. So this plot is showing the ratio of the gauge field energy density to the total energy density for different values of the coupling, alpha over F. And you can see for low couplings it's pretty boring. Parametric resonance is not enough to transfer a significant amount of power or energy to the gauge fields. However, as we increase the coupling, at some point, we don't just see effective preheating, we see almost instantaneous preheating. So this is as close to instantaneous as you can get. You get the whole energy density of the inflaton dumped onto the gauge fields within less than one oscillation of the background inflaton. So the universe becomes radiation dominated immediately. And actually it's very important to know the equation of state of the universe after inflation if you are to really map the CMB to a specific portion of the inflaton potential. So, of course, you cannot study this effect analytically, and if I haven't convinced you yet about the importance of lattice simulations, this is one more slide that I hope will convince you. So here we take three characteristic values. So a small one, 35, is like this one. 45, which is the intermediate value of the coupling, and 60, which is this red line here, this orange line here. So we artificially shut off back reaction. And what we see for low coupling, we see the blue and the red curves are the two polarizations. And as you can see, there's an exponentially big difference between them, because it's exactly what you expect to find from simple linear calculations. And if we turn on back reaction, the story doesn't change much. So for low couplings, back reaction doesn't play a big role. For 45, so increase the coupling a bit. Again, if you shut off back reaction, you still see this exponential difference between the two helicity modes, or the polarization modes. However, if you turn on back reaction, you see that the second polarization is starting to be generated. Right? So what happens is that the dominant polarization is carrying off the inflaton, producing the subdominant polarization, let's call it. And if you increase the coupling even more, going to the instantaneous preheating regime, then we see that at subhorizon scales, the polarization is roughly wiped out. So both polarizations are roughly produced equally. So this is a qualitatively different effect than the one you would get by doing WKB approximation or any sort of quasi-linear calculation. Now again, sticking to the data word at the conference description, what other data can we squeeze out of inflation? Now, so far I didn't tell you what the U1 field is, just it's a U1 field. However, if we want to do a connection with late universe physics, we'd better use some U1 gauge field that has a meaning. And what about the hypercharged field of a sound model? The reason I want to do that is because we know that magnetic fields are ubiquitous in the universe, and specifically at cosmological scales, there are large-scale magnetic fields with megaparsec, possibly megaparsec scale correlation lengths that we know due to Blazer observations. And you can, again, I can go more into how we detect them, but for this talk, all I need to know is that there are significant observational signatures for B fields with a strength of something like 10 to the minus 17 Gauss and above. So again, this is a similar plot as before. You see that for the parameters that give you, for the couplings that give you instantaneous preheating, we also get a large B field, as expected. And this is the correlation length of the B field, and we see it doesn't change much with the different runs. And the reason is because the correlation length is actually set by the Hubble scale at the end of inflation, which doesn't change much if you change the fields, so the coupling strength. Now, at the end of inflation, I told you that all the energy is dumped onto gauge fields, but we're not made of gauge fields, right? So what happens then? So if this is a U1 gauge field, the hypercharge, we know what happens. We can calculate how these things scatter into Higgses and fermions. And if you do the calculation, which is a similar calculation that we saw in the thermal inflation case, you can see that there's a very efficient transfer of energy from the gauge fields to the rest of the subatomic particles. So essentially, not only do we get instantaneous preheating, we get a plasma of charged particles immediately after inflation. Now, in MHD, in magnetohydrodynamics, there's a very interesting phenomenon called inverse cascade, which occurs where you have a helical magnetic field in a charged plasma. So what happens in an expanding universe where you have those two ingredients is that helicity is conserved as the universe expands, and that leads to transfer of power from short scales to large scales. So in simple words, that means that the B field can be protected from redshifting and be stronger today than you would naively expect it to be. And these are two plots taken by a paper by Campanelli in 2007. This shows a non-helical field, how it decays, and this shows a partially helical field. So essentially, the non-helical part initially is dumped out, and then the helical part undergoes inverse cascade. B fields, so MHD simulations in the early universe are very hard to do, and like this paper came like last week. So there are very big collaborations trying to kind of capture this phenomenon and refine them as much as possible, so we can connect actually predictions to observations. Now, in our case, I told you a few slides before that helicity is roughly wiped out. Well, let's see how accurate that is. If we actually calculate the helicity fraction of our gauge fields, it's not actually zero, it's something like 0.5, which is more than enough than we need for the inverse cascade phenomenon to turn on. And if we take into account the conversion of hypercharge to E&M gauge fields and the conversion of gauge fields to plasma, we end up with an effective magnetic field today of roughly 10 to the minus 16 Gauss. And remember, we need 10 to the minus 17 in some calculations to satisfy the Blazer observations. So this mechanism actually has the capacity to connect today's B fields to inflation and give us a very different handle on observational predictions, not from the CMB, but from the very last couple of E-fields of inflation. Now, okay, who ordered that? What other fun stuff is there? So here I plot the inflaton position as a function of E-folds. And what we can see is that as we increase the coupling, we see that the inflaton actually stops and then rolls down again. So essentially the back reaction from the gauge fields are so big that the inflaton kind of breaks and then continues. So let's look at this blue line. What we see here, this is the acceleration of the scale factor. So if it's positive, we have inflation. And what we see is that inflation stops and then starts again, right? So inflation ends momentarily. And why is that important? Well, it is important because as we know in formulations of fluctuations in inflation, usually fluctuations go like delta phi over phi dot for simple single field models, or delta rho over rho dot. Here I plot 1 over phi dot in red and 1 over rho dot in blue. So what we see actually is we see that there's a feature, a clear spike in 1 over rho dot, which signals a spike in the density fluctuation spectrum at exactly that scale. So this is a plot taken from a paper by Andre Linde, Sander Muij, and Enrico Payer. They calculated the density fluctuation spectrum by doing a quasi-linear analysis of the fluctuation and the resulting back reaction. And you see that it smoothly goes up towards the end of inflation. However, here we find something different, which is not a monotonic increase, but actually a spike. This is an example of trapped inflation, a phenomenon that has been kind of studied by Marco, among other people, in a recent paper. And this means that this spike can alter black hole production, and we have to recompute bounds on alpha over f based on features like that. Am I out of time? Yes. I'll leave you with my summary slide, and all I need to say is that it's a very exciting time to be doing inflationary physics, and we have squeezed as much of the CMB for now as we can, I think, and there's other equally interesting areas of inflation that we need to be looking and trying to find more observational handles like PDHs or B fields to probe inflation even further. Thank you very much.
Thanks, Evangelos.